Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one, continuing the series on impulse and momentum part 1, is about the conservation of momentum. We've met momentum defined as the momentum is the mass times the velocity for a particle or body. Momentum is a vector quantity and it's measured in Newton seconds. We often have to measure the change in momentum, which will also be a vector quantity, and that will be the final momentum minus the initial momentum. Remember that momentum is not the same as energy. We have two principles. The first is the WorkEnergy Principle, which says that the work done is the final kinetic energy minus the initial kinetic energy, or in shorter words, the change in kinetic energy, and the impulse momentum principle, which says that the impulse is the change in momentum. Remember that impulse and momentum are alike vector quantities and are measured in Newton seconds. When we take a collision, here's a simple case where two bodies collide in a line. All the motion is taken in one straight line, which makes it simple. We're agreed that when we model a collision, we ignore the forces which are not interaction forces, and the reason for that is that we idealize the collision as a very large interaction force acting over a very short time in such a way that the product of force and time is the impulse between the two, and we effectively idealize that by saying that it takes place over zero time, but that there's still an impulse acting. And because it's zero time, the impulses of other forces which are not expected to be large on the same scale can be ignored. So we're only interested in the interaction forces between these two. Now, if everything takes place in a straight line, Newton's third law will tell us that there will be an equal and opposite horizontal force interacting between those two bodies or particles. Now, if the force of interaction is equal and opposite, the impulse alike will be equal and opposite, because the common time between the two is all that differentiates the force from the impulse. You multiply the force by the time to get the impulse, and if the time is common, the forces being equal mean that the impulses will be equal as well. So let's put the impulses on the diagram. There we are, represented by two arrows of a different type, and the I in one case is to the left and the I in the other case is to the right, so that they are indeed equal and opposite. Now we use the momentum impulse principle in order to get some relationships between the quantities here. So in particular, if we look at the left hand particle, minus I is the impulse, and I've said minus because it's to the left, whereas that arrow tells us that positive is to the right. That equals m1 u1 minus, or rather it's m1 v1 minus m1 u1. That's the change in momentum, and for the second particle, I is equal to m2 v2 minus m2 u2. If we add those two equations together, we can eliminate the I, and that tells us that we have m1 v1 plus m2 v2 minus m1 u1 minus m2 u2. Right, now, if we look at what we've got there, we could put brackets around those two and change that to a plus sign, in which case we see that what we've got here is the final momentum, and what we've got here is the initial momentum. The initial momentum, by reading off the top from the information above the particles, m1 u1 plus m2 u2. So the initial momentum in the second bracket is equal to the momentum in the first bracket, since the difference between them is 0. So if we look at that algebra again stated here, we've ended up saying that the initial momentum is the final momentum, and so in a collision, momentum is conserved. And finally, I remind you that we assume that the collision takes place over zero time, and that's why we can ignore the impulse of other external forces. Let's look at an example here. a 3 kilogram and a 2 kilogram mass are each approaching each other at 4 meters per second, and we want to know what happens if they coalesce. Well, we'll have a common velocity if they coalesce, so we'll put that onto the diagram. There's the common velocity, and then we can apply the principle of conservation of momentum to find out what v is. So remember, the initial momentum comes by reading off the velocities above the particles and the final below. So applying that principle, we'll get 3 times 4 plus 2 times minus 4 is equal to the 3 and the 2 times the v. So the left hand side simplifies to 4 and the right hand side to 5v, so that easily tells us that v is 4/5 or 0.8. I followed my usual convention of putting no units on the diagram, but I do finish the question by answering it in context with the unit. So the combined speed is 0.8 meters per second. Now, that's not enough. You've got to say the direction, and so what I've done is said it's the same as the original direction of the 3 kilogram mass. You could equally well have said that it's in the opposite direction to the 2 kilogram mass, but some indication of direction is essential. Now let's look at another problem of a similar sort. This time we're told that we've got 3 kilograms, 2 kilograms approaching each other, and we're to find the impulse on each mass. We're given the information that it's the same problem as before. It's just that we're taking the information that we've worked out from the previous page. So this time we're interested in the impulse, and that will appear on each mass and be equal and opposite. So there we are, it's represented on the diagram. Now in order to find out what that is, we'll need to apply the impulse momentum equation to either one particle or the other. Well, as it happens, we apply it to the left hand one, but we get exactly the same result with slightly different working from the right hand one. So if we do that, we can see that the impulse, which has to be to the left because we agreed that positive is to the right, is equal to the change in momentum, the final momentum minus the initial momentum for the left hand particle. Well, that's again a few numbers, and it gives us an answer fairly quickly. It's that I is 9.6, and that has to be to the left because the I is positive. From the diagram, that means it's going to the left. So now I give my answer in context. The impulse of each on the other is 9.6 Newton seconds, and I've had to specify the direction as well, and because they're equal and opposite, we need to make clear what acts on what. So in each case, the effect of the impulse is in the opposite direction to its original velocity, and that makes it clear. Right, a slightly different problem. 3 kilograms, 2 kilograms moving towards each other at 4 meters per second. So we'll put our 2 arrows of 4 on the top, moving towards each other, and we'll have the fact that the 3 kilogram moves forwards at 0.4, and we're asked to find the speed of the 2 kilograms. So if we put that information on, we're essentially trying to find out what v is. Now if we apply the momentum conservation principle, that's the initial momentum equals the final momentum, again we read off the top and equate it to reading off the bottom. So that gives us simply enough check that the left hand side comes from reading off using the top velocities and the right hand side from the bottom velocities where v is unknown. So that gives us an equation to solve. 12 minus 8 on the left hand side is 4, and minus 1.2 gives us eventually 2.8. So our v is 1.4. If we got a v as a negative, then that would have told us that our guess that it's going to the right was incorrect, and it's actually moving to the left on that diagram. So I state my answer in context. The final velocity of the 2 kilogram mass is 1.4 meters per second, and it's in the opposite direction to the one, I perhaps should have spelled that out further, to the one it was originally, but I think that makes it clear. Now another variation on the same thing. This time we don't know what the mass of the second particle is. So again, the diagram which shows all the information given, and the principle used is that momentum is conserved. So if we write the momentum conservation equation in this case, it's again simply a matter of reading off the values above and the values below. that gives us an equation for m, which is actually even simpler than it looks because of the proliferation of zeros. So we'll end up saying that m is equal to 3, and that is the end of that question and that video presentation. The next in the same series will begin Impulse and Momentum section 2, and I'll hope to be with you later to explore that.